order to determine the energy content of a cereal. That's how all food product calorie contents are measured, through constant volume calorimetry. And so we did that. So we'll start with question number 2 from the practice test. And see, we're still just the 4 of us. And do you each have a copy of the practice test in front of you? So when I'm reading through a question, you can follow along?
Yes.
Okay. All right. So we're going to do question number 2 from the practice test. And it says 1.887 grams sample of an ionic compound, we're calling compound X, is known to contain iodide ion, I-. And the sample is dissolved in water. It's water soluble. Most ionic compounds are. And the objective is to precipitate out the iodide ion. And you're going to do that by adding an excess of one of these 2 compounds, lead nitrate or potassium nitrate. And then form a precipitate, and from that precipitate, determine how much iodide ion is in the sample, is in compound X. So we have to figure out what would be the best compound to use to precipitate out the iodide ion. If we do lead nitrate, you know, when it dissociates, we get Pb2+ and 2 nitrate ions. And if we do potassium nitrate, KNO3, this is an ionic compound as well. When it goes into water, it will produce potassium ion and nitrate ion. Now, our objective is to precipitate out the iodide ion as a solid. So which of these 2 are we going to add to that solution, to a solution of compound X to precipitate the iodide ion? And on the test, you would have a copy of the solubility table, and you would use the solubility table to determine which of these ions, lead or potassium, would be insoluble with the iodide. And it turns out, looking at that table, hopefully you can figure it out, it would be the lead. Lead and iodide ion are not compatible together in solution. They'll find one another and they'll grab hold of each other and they'll precipitate up as solid. So we're going to add excess lead nitrate to a water-based solution of this compound X in order to precipitate the iodide ion. Any questions on that? Okay. So I'm going to use a block diagram here to illustrate what's happening. So we take our 1.88 grams of compound X, and we're going to add water, H2O, and that means we're going to create and that means we'll have an aqueous solution of the iodide ion that was part of compound X. And then we're going to add excess of the lead nitrate compound, because as we saw before, lead nitrate will produce lead plus 2 ions, and they will precipitate out with the, so we have Pb plus 2 and iodide ion in solution together, and they're incompatible, and they will precipitate out as solid, PbI2, solid. Can you see that okay? PbI2?
Yes.
Okay. So any questions about where we are so far? So we take our compound X, we add water to it. It's an ionic compound, so it goes into solution and dissociates 100% into its ions. One of those ions is iodide. So we have aqueous iodide ion. Then we add excess of this lead nitrate, which will give us lead plus 2 ions in the solution with the iodide. They will precipitate out as PbI2. And the reason why it's PbI2 is because I minus, iodide ion is -1, lead is +2. We have to have an electrically neutral solid compound, ionic compound. So we're going to have 2 iodide ions for every lead. And now you filter and dry and mass that. So you filter this solution that has that precipitate, and what you end up with is, that's still on, what do you end up with? 2.2. This is 2.62 grams of lead iodide, Pb plus 2. I mean PbI2. Okay. So that's what we have. Now what you do, you have a stoichiometric problem. And what do you do in stoichiometry? You know, the 5 steps to success. The first thing you're going to have to do is define the chemical equation, chemical reaction equation. And there's only one reaction taking place here. And that would be right here in this step. The lead iodide, Pb plus 2, is reacting with 2 iodide ions to form PbI2 solid. Okay? So that's the reaction. We're doing the stoichiometry now. Stoichiometry. And step 1 in stoichiometry is write out the chemical reaction equation of interest that's at play here. Any questions on that? Nope. Okay. And the next thing we do is to convert whatever we have, whatever mass we're given or volumes we're given, convert it into number of moles. Now, the only thing that we're given that we could that we can convert into number of moles is the mass of this product, lead iodide. So we take our 2.62 grams of PbI2, and we're going to multiply it by the fact that there is 1 mole of PbI2 for every 461 grams. Right. So how do we get that 461 grams? Well, you look on the periodic table, look up the weight of lead, molar mass of lead, and the molar mass of iodide, add them together, you get 461 grams. Grams cancel, and we're left with the number of moles of lead iodide, which is 0.0057 moles of PbI2. Okay. That reading correct? Okay. 0.005257. Okay. Now, step 3 in a stoichiometric problem is to find the limiting reactant. And what is the limiting reactant in this reaction? Here are 2 reactants. One of those 2 is going to be limiting. We have the lead and we have the iodide. Which of these 2 gets used up first? That would be the limiting reactant. It's the iodide. How do we know that? Because we added excess of the lead. We added a whole lot more than was necessary to precipitate all that iodide ion. So the limiting reactant is I minus, the iodide ion. Step 4 now is to determine how many moles of iodide ion we have, because that's what we're trying to answer here. How much iodide ion is in that compound X? I hope I said that at the beginning. That's the whole objective, to determine how much iodide ion is in compound X. It's a how much problem, and you know how much problems are stoichiometric problems. So now what we're going to do is take our 0.0057 moles of PbI2 and multiply it by something that'll convert it into moles of iodide ion, the thing that we're interested in. And that's why we have a balanced chemical equation, reaction equation. That's why we need that in the very first step. This tells us the relationship between the number of moles of lead iodide and the number of moles of iodide ion. And this tells us for every mole of lead iodide we have, excuse me, we require 2 moles of iodide ion. So we're going to multiply this 0.0057 moles of lead iodide by 2 moles of iodide ion for every, let me get rid of that. We have 2 moles of iodide ion for every 1 mole of PbI2. And so the moles of lead iodide cancel, and we have to multiply through by the 2 there, and we get 0.0. Now the board's getting floppy when I get down here in the corner. It's hard to write on it. It starts moving on me. But that's how many moles of iodide ion are in that compound X. Are we done with the problem? Nope. We want to know how much in grams. I didn't state that. So that'll be the last step. We take our 0.011 moles of iodide ion, and we'll multiply it by something to convert it into grams of iodide ion. And that something is simply the molar mass of iodide ion and of iodine. And that is 127 grams of iodine for every mole of iodine or iodide ion. And so the moles of iodide ion cancel, and we have the number of grams, and it turns out to be, drum roll, 1.44. And that would be the answer to question number 2 on the practice test. There's 1.44 grams of iodide ion and our 1.887 grams of compound X. And if you wanted, you could convert that into percent mass. And I think I did it on the practice test solutions, although the question didn't require that. It would be good to know that. And that would be taking your 1.44 grams of the iodide ion that is in the sample divided by the total mass of the compound X and multiply that by 100, and that would give you the percent mass of iodide ion in the sample, and it's 77% iodide ion. So that's question number 2. Are there any questions on that? Concerns?
I have a question. I don't know if you can hear me properly.
I do, I hear you.
Okay. So at the beginning, I don't understand. Could you repeat why you decided to choose lead?
Lead nitrate. That's a good question. It's an important question or important point in the problem. I'm going to give myself some space here. Okay. This is lead nitrate, right? And you put it into water. It's an ionic compound. Is that showing up there? No. It's an ionic compound. So what do ionic compounds do when you put them into water? They dissociate 100%. So it's going to dissociate into these ions, right? Now, what is special about lead with respect to this problem? In this problem, our lead +2 ion is incompatible with iodide ion in water-based solution. It'll precipitate. And that's what we want to do. We want to precipitate all of the iodide ion that's in this water-based solution of compound X. We want to precipitate it out as a solid so that we can mass it and determine how much iodide ion is in there. So we need to add some compound that will precipitate the iodide ion. And remember this solubility table? Does this look familiar?
Yeah, so you just took that information from the table, right?
I did, yes.
Oh, okay.
You look at that table and you'll find that lead and iodide ion will precipitate out. They're insoluble together, right? So that's where it came, from where it came.
Yeah.
Okay,
Thank
any
you.
other questions?
I have another one.
Good.
At the end.
Yeah, if you do, and others who have the same question.
Yeah, so at the end, in step number 5, you're just going back from moles to the mass of the iodide and ion, right?
That's exactly right. We calculated in step 4 that we have 0.011 moles of iodide ion. What we want is the mass of iodide ion. So we take those number of moles and we just multiply it by the molar mass of the substance. Our substance is iodine, multiplied by the number of moles by the mass per mole of iodide, and we get grams.
All right. Thank you.
You're welcome. Any other questions on this problem? Okay, we're going to move on to question number 3. Now, this is a time-consuming part on this crazy board because it's floppy. It takes a while to erase it, and it's a small board, so I can't move on to other spaces. Have to erase it after each problem we do. But all right. Okay, so now we're going to do question number 3 on the practice test. And we have this particular equation, or reaction. We have NH3, make sure that's showing up. Let me, ammonia plus HCl, hydrochloric acid, reacting to form NH4 Cl, ammonium chloride. So this is a gas, and HCl actually is a gas if it's not dissolved in water. And these two gases react and they form this solid ionic compound. This is ammonium chloride because NH4 plus is ammonium ion, Cl minus is chloride ion. And we know the heat of this reaction, the enthalpy change. You're told that the heat of the reaction, which is equal to you're given that negative 92.5 kilojoules. Okay, can you guys see that okay? Okay, so that's what we know about this chemical reaction. NH3 plus HCl. Oh, we don't know that. I'm sorry. My bad. What we want to find out is what is delta H of this reaction. Sorry about that. We don't know what it is. So we need to find out what it is. And we can do this through an indirect way called Hess's law. And what on earth is Hess's law? And this was talked about in one of our video lectures. And Hess's law is basically saying that, let's say we have, here's our NH3 plus Cl plus HCl. And nature does this directly, right? The NH3 and the HCl collide with one another, and they react, and they form this new compound. And you'll get a very specific heat associated with it. But it turns out that heat energy, delta H, is a state function. And what it means to be a state function, it means it doesn't matter how you get from the initial state to the final state in terms of the value of that property. All that matters is that you start at the same place and you end at the same place. So we could do, nature does it this way. Let's say this is path A that nature takes, a direct combination of NH3 with HCl to form ammonium chloride. But we could do it in this different way. We could take an alternate pathway. And as long as the initial state is the same, and call this path B, and the final state is the same between these two, we can say that delta H of path A will have to be equal to delta H of path B. They have to be identical. Why? Because we start and end in the same places for each pathway. So what we're going to do is not react this the way nature would and just create this directly from the collision of ammonia molecules with HCl. We're going to take an alternate pathway. And we're going to use the three equations that are given as part of this problem to create that alternate pathway. So the three equations are going to be, they're listed there. We have HCl, is that on the board? Reacts or goes to 1/2 H2 plus 1/2 Cl2. And we know that the heat of this, delta H, that is provided, is equal to negative 92.5 kilojoules. And we're going to call this, let's say, reaction A. And then you're given a second reaction. We'll call it reaction B. And that reaction B is we have 4 moles of hydrogen gas plus nitrogen gas plus chlorine gas, Cl2, will react to form 2 NH4Cl. And you're given the heat for that reaction. Now remember, it's important to remember that heat energy is equal to the enthalpy change. Delta H is enthalpy change, and under constant pressure conditions, the change in a system's enthalpy is exactly equal to the quantity of heat energy it exchanges with the surroundings. Okay. And we're told for this reaction, that second one that we're calling B, it's equal to negative 628 kilojoules. And then you're given a third reaction. And the third reaction is nitrogen gas, N2, plus 3 hydrogen gas, H2, goes to NH2NH3. And you're given the heat for that reaction as well. That is equal to negative 92.2 kilojoules. So what we're going to do is to use these three reactions to create this alternate pathway. Nature does it in one direct step, right? Bang, bang, bang. The NH3 hits HCl, produces NH4Cl. We're going to take this alternate multi-step pathway, and we're going to use these three equations to create that alternate path. So how are we going to do that? Well, we know that we need 1 mole of HCl as our reaction. So we're going to recreate this balanced chemical equation using these 3 reactions, and we need 1 mole of HCl. So we look at our 3 reactions and we see equation A has 1 mole of HCl. So we're going to use, take A and write out HCl goes to 1/2 H2 plus 1/2 Cl2. And we know that the heat of that reaction, delta H, is equal to negative 92.5 kilojoules. Okay. And that'll give us our HCl. We have to have that. 1 mole of HCl as a reactant. Now, what else do we, man, we only have 10 minutes left. Gee whiz. What else do we need? We need 1 mole of NH3. And is there anything here that has NH3 as a reactant or a product? Well, equation C has 2 moles of NH3 as a product, but we need 1 mole of NH3 as a reactant. So we're going to reverse this reaction and divide it by 1/2 so that we'll have 1 mole of NH3. So we take negative B divided by 2. We're going to take this reaction, is that the one, or which one are we? NH3, oh no, negative C. We're going to reverse letter C. We're going to take this reaction and reverse it and divide by 2 so that we'll get 1 mole of NH3. So we'll have NH3 as a reactant going to 1/2 N2 plus 3/2 H2. And now what are we going to write down for the heat energy of that? Well, the heat energy for equation C is negative 92.2, but we reversed it, so it's going to be positive 92.2. And then we divide it by 2, so it's going to be positive 92.2 divided by 2. And that gives us, so it would be negative 1/2 times 92.2, negative that, and we get so we'll just keep it at that right now. We reversed the reaction, so that's going to make the negative, reverse the sign of the heat, and then we divide by 2 in order to get that 1 mole of NH3 as a reactant. And so we have that. So we have our 2 reactants, 1 mole of HCl reacting with 1 mole of NH3. We need 1 mole of ammonium chloride. And we'll get that because ammonium chloride is equation B. But notice we have 2 moles of ammonium chloride. So we're going to take B divided by 2. And that will give us 2 moles of ammonium chloride as product. So that'll be equation B divided by 2. It's going to give us 2H2 plus 1/2 N2 plus 1/2 Cl2 goes to 1 mole of NH4Cl. And that gives us the 1 mole of ammonium chloride that we need to recreate that balanced equation. Now, what have we done to equation B to get that? We've divided it by 2 to get that 1 mole of ammonium chloride. So we divide its heat energy by 2. So we'll have negative 628 divided by 2 kilojoules. These are kilojoules. Now, the last step is to simply add up these 3 reactions. And you cancel everything that cancels, and the only thing you'll be left with are these circled items. Notice we have 1/2 H2 plus 3/2 H2 on the right side of the reaction arrow, and we have 2H2 on the left-hand side, so those cancel. We have 1/2 N2 on the right-hand side, and we have 1/2 N2 on the left-hand side of this one, so those cancel. And we have 1/2 mole of Cl2 on the left-hand side and 1/2 mole of Cl2 on the right-hand side. So those cancel. So that what you're left with is simply HCl plus NH3 gives NH4Cl. And notice that's the same reaction that we have up here. But we've gotten there through a very different pathway by adding these things. Nature does it directly in one step. We've done it through 3 steps of adding up these different reactions. Now to get the heat, all we do is add up the heats from these 3 steps. And if we do that, we get minus 360 kilojoules. Minus 360 kilojoules. And that is the answer for question number 3. This reaction, the heat of this reaction is exothermic. It's minus 360 kilojoules. Okay. And the reason we can do that is because enthalpy change, which is the heat energy, is a state function. And all that matters in terms of the change of that, the change in the enthalpy, is where you start and where you end up. And notice by adding these 3 reactions together in the way that we have them established here, we start at the same place and we end at the same place. So delta H will have to be the same for path A as it is for path B. Path B is what we did here, and path A would be the direct route that nature takes. And so we know the heat of that reaction. Any questions on that? I think we did a example of that in the online video lectures. Questions, comments? Can you see everything okay? Did it show up all right? Okay, well then we'll go to question number 4. And question 4 is a titration problem. And let's see, need to. So question number 4. We have 1 gram of some monoprotic acid. So that's 1 gram of monoprotic acid that's dissolved in water. So that is our aqueous solution of this 1 gram of acid. And what we want to know is what is the molar weight of that acid? And that's the objective. So what we do is a titration. So we take a burette and we take a 0.25 molar solution of NaOH, sodium hydroxide, and we add that dropwise into our solution of this acid. Okay? And this is our 1.0 gram of HA with some water, dissolved in water. And we also have an indicator in there, an acid-base indicator, like the phenolphthalein that we used for our acid-base lab a few weeks ago. And it is found that 19.6 milliliters of the NaOH was required to hit the endpoint for the color change. And now we have enough information to solve this problem, to answer the question, what is the molar mass of that acid? And this is a stoichiometric problem. And step 1, stoichiometry, 5 steps to success. Step 1 is to write out the chemical reaction. And the chemical reaction is That is the balanced chemical equation. We have our monoprotic acid. Monoprotic means it only has one proton it can donate.